You're not being told the whole truth when it comes to recycling, and composites are no different. What I'm going to be doing in this video is I'm going to be going through the different techniques and the processes of how do you actually recycle composites. And I'm also going to be telling you the things that manufacturers are not telling you when it comes to recycling these materials. So let's get into it. So the first thing to go into would be to look at the global recycling stage. And the reason why I wanted to do that is I wanted to paint you a picture of what does successful and good recycling look like, and then do a comparison of composites and how to actually bring that into composite and make it viable. So first thing first is when you look at this list, what you will see is you will see at the top a bunch of metallics, where you have the global production rate, for example, of steel is very high, as you'd expect. But on the recycling rate column, you will see that the metallics are getting recycled so well, but glass and carbon fiber, the composites, the recycling rate is almost non-existent. I decided to choose aluminium as an example of good recycling to expand upon. Aluminium is very expensive to extract, and the reason for that is the process of extracting aluminium just requires so much electricity. As an example, if you were to take a comparison between recycling aluminium and extracting it from the earth, recycling aluminium takes only 5% of the energy compared to extracting new aluminium from the earth. Now, because aluminium is such a valuable product, therefore it gets recycled a lot, and out of all aluminium ever made, 70% of it is still being used today and is still in circulation. So that's how valuable the product is. And then the same thing, to be fair, also applies with other metals. And another opportunity with aluminium is kind of material which is infinitely recyclable. You can just recycle it over and over again. So what's the takeaway? Now, what does it take to be successful in recycling? The value of the end product needs to be higher than the recycling effort. In really layman's terms, what it is the output, the product that comes out of it, there needs to be a business case where you make more money from that product than the effort that has gone into extracting that product. So what about composites? Composites are more complex because composites are made of different materials. In our case, what you're looking at the screen here is you're looking at a continuous fiber, which is encased in a resin. And therefore, how do you recycle these? Well, you need to break it into the different parts and then look at the components. So first thing first, resin. So the resins, the different type of resins, you have Thermoset resins and thermoplastic resins. And the fiber, you have the likes of natural fiber, glass fiber, and carbon fiber. Now that's very important. It's very important for the fiber because the fiber is usually where the value is at. So when it comes to fiber, natural fibers, people use them because they are very low in carbon emissions. Now, if you were to recycle a natural fiber, at the end of it, the end product will be so low in performance that it would not be economically viable. Now, if you go into other stuff such as glass or maybe carbon, well, glass is more valuable, carbon is very valuable. So if you want to make a business case and make it economically viable, carbon is a great product to actually use and to extract, simply because it has a lot of inherent value into it. Now, when you look at the resin is where the effort that it takes to remove the resin out. I thought I'd put a bit of emphasis into the resin types. This here came from the first video on the fundamentals of composites. If you haven't seen that video, go and watch it. There'll be a lot of surprising content that you will see in there that most people don't tend to cover. But I thought I'd cover it here as a refresher really quickly. On the left, you have thermoset material. Thermosets are what you call conventional composites. And conventional composite just means that thermosets are just being used almost everywhere right now, so that is the most used material. With thermosets, the material, when it cures, it cross-links. So the analogy here is it's a bit like an egg, where you cook an egg, you cannot bring it back into its liquid stage. When it's cooked, cross-links are formed. The other type of material that is maybe getting used more and more now are called thermoplastic composites. And thermoplastics, you just melt it. You can remelt it quite a few times. So it melts, solidifies quite a few times. So the analogy is a bit like butter, where you can melt and reform it a few times. That difference really matters when it comes to recycling. Let me explain. With a thermoset, because it is permanently set after you've cured it, if you want to recycle it, you have to remove the resin. You just have to remove the resin. Whereas with thermoplastic, because you can remelt it over and over again, you can actually reuse the resin. You don't necessarily have to remove the resin. So let's bring our eyes then into how do you remove resin. So there's two ways of removing resins. To the left here, you can see pyrolysis. So pyrolysis is the thermal decomposition of polymers. So you take whatever material you have, you put it into a pyrolysis chamber. And if you apply a lot of heat into it and remove oxygen, because you don't want oxygen to be oxidizing your polymer, what happens is you can actually remove and degrade your resin out of the fibers, and that's how you recover the fibers. The other way of doing it is solvolysis. So solvolysis, what you're doing is you're using some very harsh and powerful chemicals, which will over time break these powerful bonds and therefore remove the polymer. Now, I thought I'd do a bit of a comparison between these two processes. Let's look at pyrolysis. So pyrolysis, the process itself, the output of it is you get fibers, and the fibers are of moderate quality. So you can use it in quite a few applications, but also the secondary output of it is the resin becomes pyrolytic oil or gas. So it's the kind of thing that you can use for energy generation, and actually pyrolytic oil, you can actually convert it into things like jet fuels, which is useful. And the next one, when you compare it to solvolysis, is in solvolysis, the fiber quality is a lot better than pyrolysis. And the resin, what happens to it is the resin becomes very simple resin monomers, which can be used to make some more plastic component. For sustainability, if you were to look at pyrolysis, well, the gas emissions are actually really strictly controlled there, especially in Europe. And you compare that, say, to solvolysis, well, you're using some very harsh chemicals in quite high volumes. Now, if you want to scale these processes, pyrolysis can be easily scaled in an economy where you have a lot of energy available, not Europe. And if you were to compare that to solvolysis, solvolysis is a lot more challenging to scale up. And that's just because you require so much volume, and the processes, there's some economies of scale, but it is a lot more challenging. And that's where the cost comes in. Because you can really scale pyrolysis, the cost is low, especially where energy is relatively cheap in these countries. Whereas if you compare it to solvolysis, well, getting the amount of solvent there is just quite an expensive process. With thermosets, you have to remove resin just because the material, once it's cured, it just stays there. But with thermoplastics, you can actually remelt that resin and reuse it. So the recycling of thermoplastic is a lot easier. Let me explain. With thermoplastic, what you're doing is you're taking your waste, which could be from manufacturing process, or it could be at the end of life. And what you're doing is you're shredding that big component into smaller components. And these smaller components can now be remelted. So in this case, you can compression mold it, or you can even add some more material to it, say some more virgin resin to it, and then you can injection mold it into a mold as an example and get a component out of it. So that's the opportunity here with resin reuse, where these previous processes were so requires so much energy and effort. With thermoplastics, you just break into smaller pieces and then you can repress it into a new shape, which is quite an opportunity. I have a picture here. You can see on one side you have a virgin carbon fiber surface, so that's an A surface, and then on the other side of the bracket you can see they are actually using a recycled material. So when you're using recycled material, you can use 100% recycled or partially recycled, and in this case the A surface, the surface that say the customer will see, will be a beautiful virgin surface. So as you can tell, a lot of composite really focuses on fiber recovery. Now, thermoplastics, you can just reuse the fiber, which makes it a lot easier, but both of whether you're removing the resin or reusing the resin, most of these processes, what happens is the fiber orientation in the original part becomes randomized, and you are shortening the length of a fiber in most of these processes. And I wanted to maybe delve into what happens when you shorten the length fibers. So I have this chart here, and what you're seeing is at the bottom on the x-axis are different fiber lengths, where at 100 you can consider it to be a continuous fiber, and then as you go more to the left, the fiber becomes shorter. And then on the y-axis, you just kind of have a comparison of how the fiber length impacts the performance. So you can see that the shorter your fibers, the first thing that is impacted is, well, actually, your impact resistance becomes lower, and you also have affected the strength and then the stiffness. So that's what happens when you recycle composites. The shorter the fibers, the more these properties are being impacted. So if you look at the picture here, you have an injection molded component where on one side, what they have done is they have removed the resin, and then you can see kind of like the short glass fibers. Now, when it comes to different manufacturing processes, what is interesting is if you're injection molding, usually you're using short fibers. The reason for that is when you're injection molding, you're pushing the material through a nozzle into a mold. So there's a lot of material movement. And if you have really long fibers in there, these fibers will just clog up and never fill your mold. So that's why you want shorter fibers. And then also as it moves through the mold, the fibers are breaking and so on. And it makes it a lot more difficult to fill your mold. Compression molding, on the other hand, is different. Compression molding, what you're doing is you're taking your material and you're placing it directly into your mold. So when you're pressing that material, there is a lot less material movement. And what it means is with compression molding, you can get away with much longer fibers. Therefore, you can get much better performance when it comes to material properties. I thought I would include a picture here. They were formerly known as ELG and now it's called Gen 2 Carbon. And this is just a line of their products where you can see at the bottom there, they have some mill fibers, so very short fibers. You can use it as fillers for injection molding and whatnot. And as the lengths of these fibers go up, then you can do compression molding and so on. But eventually what they can also do is they can turn these fibers into a matting. Now the matting is really interesting because the matting is a big mat of non-woven discontinuous fibers. They go in different directions and of a certain thickness. So that matting could be quite useful in certain, say, compression molding applications where you can drape your fibers around. But what we've been seeing lately is a lot of recycling companies, what they're doing is they're finding ways of reorienting the fibers. So if you take the fibers and then they reorient the fibers in one direction as far as they can do that. And then what you have is you have a product which is a kind of unidirectional product. So therefore it's very strong in a particular direction. And therefore it makes it a high value recycled product. As you can tell, there are a few technologies that can enable the recycling of composites, and there's a lot more in the pipeline. One of them is pyrolysis, where you can use steam to recycle, and that's going to be its own video because it's so cool. Generally right now, because most of the industry is Thermoset based, as in the material is cross-linked, it's quite difficult to break it. So you have to use these expensive technologies. At the end of it, what we're going to be seeing is companies are going to be focusing on the expensive stuff. carbon fiber as an example. Carbon is worth a lot, so we're going to be focusing on that to start with. But then you can think of the energy industry where we have so many wind turbines out there, and at the end of life right now, all our wind turbines are going into landfills. Not very sustainable. So the energy industry is going to start focusing on removing the glass from these end of life wind turbines, and then the glass is going to go into, say, construction and that sort of industry. So that's another industry where we're going to see a big amount of change. That being said, all these industries, you still have to put the effort into solvolysis and pyrolysis. But when it comes to thermoplastics, you don't have to remove the resin, you just break it into smaller pieces, and then you can just put it into a new mold and press it again. So thermoplastic is going to completely change the landscape of recycling composites because it's so much easier to recycle. You do not have to remove the resin out of the fiber. It can just stick together and then you turn it into another component. I hope that you enjoyed today's overview on recycling. If you haven't clicked on the subscribe button, do it now. There's a lot more coming, especially in recycling. And in the meantime, I wish you well. Peace.